Right, hello everybody, my name is David Freedman. I work for a company called Claranet. We operate in a number of countries in Europe. Unfortunately, we don't operate in Scandinavia or the Nordic region. And I'm here to speak about secure IDR, what that is, what that means for us, what's being done in the IETF. And I'll start with this, which you can't see very well, and I suspect this is intentional. The Secure IDR Working Group is a working group of the IETF. What that means is it's a set of people who end up being chartered to perform work that ends up possibly being standardised. And they're called Secure IDR, and IDR stands for Inter-Domain Routing. Now, the Inter-Domain Routing Working Group of the IETF look after routing between domains, such as autonomous systems in this case, and this means essentially that they're chartered with working on the BGP4 protocol. So the IDR working group work on the BGP core protocol. They don't deal with peering or how the BGP protocol is used. They just focus on the protocol itself and its semantics. Things such as peering and internet exchanges and everything else associated with how the protocol is used falls under the remit of the GROW working group, the Global Routing Operations working group. And SIDR, the Secure IDR working group, are chartered with securing inter-domain routing. So working on ways to secure the routing semantics between domains, between autonomous systems. But they don't modify the protocol itself. If SIDR suggests that parts of the BGP protocol need to be changed, that has to go to the IDR for approval. So what happens in the SIDR meetings is that the drafts, internet drafts that are written, that are being looked at or possibly being worked on by the SIDR working group are discussed at the meetings, which happen at IETF meetings, there are multiple IETF meetings a year. This photo was taken from the last one, IETF 81, which was in Quebec. And I've said at the bottom, you're in a darkened room at the IETF, and it was quite dark. You're surrounded by vendors, because most of the people that attend these meetings are standards people. Most of these people work for vendors, for the manufacturers of the routers, routing devices that you use. And a lone operator stands quietly in the corner, and this refers to the fact that there are not many operators that are in the IETF or that work in the IETF. I can think of a handful that I know of that work on topics that are related to operations, but essentially there aren't many. We're underrepresented in terms of operators there, and this is kind of a problem, because if you let vendors and standards people go off by themselves, they'll end up developing something that they then come and sell to you that you might not want, or may be too expensive to implement. So this talks about what happened at the last IETF IDR meeting in Quebec. But before I start, I'm going to cover some base topics to bring everybody up to speed about BGP and routing security. And I'm going to start with some really simple concepts about IP numbering management, which is that the IANA and the numbering authority, they give numbering to the regional internet registries, and you as a local internet registry consume those resources. The regional internet registries provide databases, whereas the IANA really provides a text file. So the regional internet registries provide these databases and they're of resources and who owns them, and you then consume these and you build filters with them. And I'd just like to see a show of hands quickly. Who uses routing registry databases to build filters? Put your hands up.
Cappella event is the only one. Oh, there's Raymond.
Put your hands up, everybody. And I'd like you to keep, for those who put their hands up, I'd like you to keep your hands up if you use those filters to filter peers as opposed to just customers. Not at all. Why don't we filter peers? It can be complex, can't it? So this is simple filtering. I ask a question: which routes should I accept from my customer, AS8272? And it's quite plain. If you're using the right database, you can see there's a route object. And the route object has an origin of 8272. And this has been verified by the fact that this range of addresses has been allocated or assigned to somebody with the correct set of authorities to generate this route object. Okay, and you use this route object to build a filter. But I have it too easy in this example. Firstly, this customer has no downstreams, so I don't have to evaluate any macros. And secondly, I'm only filtering a customer, I'm not filtering a peer. You try and do this with peers, then you run into data quality issues. Not all peers can be assured to use the database services to publish this information. Not all peers will be in the right region, or not all peers will use the database. If they're a customer, you've got more control over them. I'm not going to sell you this service unless you have your objects registered in the database. With a peer, it's harder to do. And also, the fact that I do this in the RIPE NCC region, I actually have a database. We don't really have this outside of the region. We have the RADB, which is very close, as in it mirrors databases such as the RIPE database. But really, if you look at these independent databases like the RADB, we lose the authority. You know, we lose the fact that the RADB brings in a number of sources, including paying customers of Merit themselves. If you pay Merit, you can put, pretty much whatever you want in the RADB, as long as you're a paying subscriber. And then there's also the AltDB, which is nice, but it's a volunteer effort, and it's not maintained as well, in my opinion, as the RADB. We don't have this really great binding between the IP resources and the autonomous systems that we have on the internet that use them when you go outside of the RIPE NCC region. It's hard. So, why do we need to filter anyway? We should just trust each other, right? Route hijacking is commonly cited as a reason for filtering, and there are two examples that you'll hear given today with regards to route hijacking. The first of which is the famous Pakistan Telecom versus YouTube. In 2008, the Pakistani government asked ISPs to filter YouTube because there was some content that they didn't like. Then Pakistan Telecom issued a /24 redirection to try and dump the traffic as it hit local ISPs that were traversing Pakistan Telecom. And then this propagated to their upstream PCCW, who then shared it with the rest of the internet. And because there were no filters, there was a battle of the longest prefix match with YouTube, trying to inject /25s, and because everybody filters on 24s, or most people do, it didn't really work. And then there were mails to operator lists. This is what's happening. Can you filter it? We had people sitting there going, filter, manually filter on places that we couldn't filter peers because they didn't have the published policy. And even more scary than this, there's the Cappella Peloso attack. And that was also demonstrated at DEF CON in 2008, where you can craft an AS path and you can take advantage of the behaviour in BGP, the loop prevention mechanism, where you don't accept updates that in the AS path contain your own AS number. So by injecting, by putting in the AS path references to ASs in the middle, you could effectively blind those networks from seeing the hijacked prefix, and then that could be used to return the traffic to its rightful destination. You had a good man in the middle there stuff. So the problem is, we need to verify the peer against the route and the AS path somehow, and we can't do any of this without good authoritative data. The system's also got to be easy to use, and it's got to be widely adopted, but most importantly, it's got to scale. So that's where we start. So, RouteSec. It's all based on the X509 certification hierarchy. This draft produced by the SIDR, called SIDR Arch, talks about how the X509 certification hierarchy is extended to be able to talk about this sort of information and be able to use it to secure some of these resources. Now, RSC 3779 introduces extensions to the certificate to allow you to talk about IP resources and autonomous system resources inside a certificate that's issued, say, by a certification authority. And another RSC 5280 talks about subject information access, which defines where this sort of stuff is published. But effectively what happens is that the IANA at the top is a CA, and it issues certificates to enable the RIRs to become CAs, which in turn issue certificates to make an LIR or a resource holder their own CA. And that's where the CA chain stops there, at the third beige box. The next thing that happens is the CA, which is in the LIR or the ISP, issues an entity certificate, right, which is a certificate which can sign objects but can't make any further downstream CAs. And then this certificate is then used to sign, make a signed blob of information that describes the resources that are authorised. Yeah, right. The binding, the exact binding we talked about between the IP information and the autonomous system. And this lets us validate the origin. And this RPKI infrastructure lets us hold databases and publish databases that talk about how the origin of a prefix is mapped to the prefixes themselves. And how do we validate this? Well, IETF CIDR RPKI router describes an RPKI router. Now these things don't actually validate origin information on the fly. They don't speak to these databases and pull these things down in real time. What happens is a separate offline system, if you like, downloads an entire copy of the RPKI. And it actually, RFC 5781 specifies this is done with rsync, which is nice and convenient because we all understand that. So this validation is done offline, and we use it to build a trusted cache of prefixes and the origins that we trust. And then the router pairs with this cache using the RPKI router protocol, and it receives trusted origin data. This sounds very futuristic, doesn't it? But Cisco have some proof of concept code in IOS and ISXR, and they have demonstrated that the compute load for each update of validating against this cache can be as low as 10 microseconds. Okay, so it's quite a bold statement. And how much of this do I need to run myself? Well, you know, you could run the trusted cache. Right? If we talk about the certification and the do you issue the certificate yourself? Well, that can be offered as a hosted service. The YPNCC have, and I'm sure a number of you have been following this recently, have a system whereby they'll host the CA for you, and there's a web interface. You can generate certificates, you can generate the rowers, and then that's it. You don't have to do the work yourself. Alternatively, you can build your own platform to do it. Same with the cache. There's an example cache at the moment. I think it's called Arsenic, and you can run this yourself. You know, or there's possibly an option for having your upstream running for you. Maybe that's a new business model, right? Where you don't have to worry about that stuff. You trust your upstream enough to let them do it for you, and you just pair your routers with their cache. So ultimately, somebody publishes it, it's pulled into the cache, and the router pairs with the cache to validate the assertions made about the stuff it's seen. But what do we do with this data? Well, it's still going to be a local operator decision. IETF Cider Origin Ops draft talks about what decisions we can make as an operator to look at these prefixes. And here's an example from an implementation, which is that we can take in a prefix and we can say, did it validate against the cache? What do we do with it? If it doesn't validate, we can drop it, we can depreference it, we can do all sorts of things with it. Ultimately, it's a local operator decision. And the mechanics have to be there for a router to take this information and make decisions on it. And these decisions could be traffic engineering related, you could just drop it. Ultimately, there's no insinuation that there's any form of implied control. And yes, trust issues do exist at the moment. The idea that the RIPE NCC or the RIR go from being somebody who don't have direct control over the routing information, i.e. if you choose not to filter using the RR, then they're effectively not telling you what to do, to going to your routers are now making decisions based on the stuff in this database without, you're effectively entrusting this to the NCC. And this is outside the scope of this presentation. This is a separate discussion. How much do you trust the upstream CAs to make these decisions for you when you're going to be making these validations, and what are the implications of that? But yes, ultimately the idea is it's a local operator decision, and that control shouldn't be removed from you. But there's a gap in this, of course. If we only validate the origins, then people stepping in the middle can take routes that are valid as per the RPKI and then manipulate them and inject themselves in the path. And this is where BGP-SEC comes in. Without AS path filtering everywhere, prefixes and their origin ASNs can still be hijacked, right? And the rubber's still valid. So we need path validation in BGP as well. So Cider have developed what they call BGP-SEC, which is the latest iteration of this path validation. There were a number of them in the past, such as SOBGP, SBGP. This is the latest iteration, BGP-SEC, and this is what Cider Working Group are working on. BGP-SEC introduces a new type of certificate issued by the CA, a router certificate. That's defined in BGP-SEC overview as well. And the keys published for the AS. So you publish this key for when an AS hands off a path element to another AS, this AS key signs it. Now ultimately every router that propagates this information through the AS, including any route reflectors that you might have, also have to do this signing. And a number of questions arise. Do you have a separate key per router? Do you share one for the AS? If you have a separate key per router, do you need to hide this from neighbouring ASs? All of these sort of questions. And that's defined in the overview document. But the idea is generally that the routers use their private keys to sign the AS path elements, and they dump them in a new BGP attribute called BGP-SEC path signatures. Now, of course, adding a new attribute has to go to IDR. It's a protocol change. But this is what the attribute looks like, in that the things that are elements that are in the AS path attribute are mapped to the BGP path signatures attribute, whereby you have each element and then a signature, the next element and then a signature. Sounds good in practice. There are still some questions that really haven't been solved yet by the working group, such as how do we deal with prepends? What happens when we add prepends in the path? Do we add the compute load to sign each prepend element? One idea that's been touted at the moment is this concept of p count, which is just a counter for how many times you want the AS path to have seen this prepended. And then you can validate against that number of prepends, and you don't have to, add the signatures to it and then potentially make it bigger. But also then what happens with these transparent root servers? GROW, the Global Routing Operations Working Group I was telling you about, have a draft at the moment to talk about the operation of root servers and how they work. And it talks about the transparency of root servers. I believe there's going to be a lightning talk later about the TREX root servers in general. But just to summarise quickly, with the transparent multilateral peering, everybody peers with them, the roots are redistributed back so people don't have to set up adjacencies with each other. And the transparency part of this comes from the fact that if you introduce this other AS in the middle, the paths look longer and you have traffic engineering problems and it's less preferable. So the transparency requirements that were put in by the GROW draft is that when something is, you peer with the root server, but when something is handed off to another peer, the root server's AS is removed from it to keep the path the same length as it would have been as if you'd had a direct adjacency. This, of course, causes a problem if we're going to assign these path elements. And the only suggestion that's been made at the moment is, well, if we've got this p count, we'll make a special case p count 0, and then this means ignore this AS path, and we don't have to worry about it. But of course, as you can see, and then non-BGP sex speakers then can ignore that completely. But as you can see, that creates a bit of a vulnerability, doesn't it? If you've got, if you've got a special flag that you can say, yeah, just ignore that, it's not signed. It's not really ideal, is it? As you can see, these two aren't actually drafted at the moment. They're just being discussed. Sorry.
What about these transition ASNs for 32 bits and the old?
AS 16-bit versus 32-bit AS. Yes, I mean the same thing applies to AS4 path as well. Okay.
Specifically referring to AS 23456.
Oh, I see. Well, if you don't have a yes, that one's not been solved either. If you don't have an AS4 path to validate against, you're going to see this unvalidated 23456 in the middle.
Is there anyone can imitate 23456?
Of course they can, yes. Now, whether that's a problem of general, that's a problem that exists at the moment, right? If you don't support the AS4 path attribute, i.e. whether these 32-bit ASs are carried as elements, then you're going to be blind to whatever happens in the middle anyway.
Well, plus you're certainly not going to support this.
Exactly. This is really intended with AS4 path in mind. The 23456 problem hasn't been solved either. But this is just to show you some of the challenges that they've got at the moment. It's far from done. And what about replay attacks? Now that has been discussed, right? If you sign a part of the path, you can replay that. Say somebody disconnects from you because a commercial agreement has broken down, but you still want to influence traffic. You're an evil operator in the middle. You might want to replay some of these previously signed announcements, right? Some of these previously signed elements. And there also might be a technical reason for it. There might be bugs in router implementations and some of this stuff might be stuck. So how do you deal with previously valid signatures that are now no longer valid? So freshness is critical. We could shrink the signing lifetime and then the origin could re-announce that before it expires to make sure that we don't get a gap. They call this beaconing, right? But beaconing comes with problems of its own. So they've suggested beaconing periods of days, but it could be hours, for instance, for critical infrastructure. And of course, the timing is jittered such to distribute the load effectively. And you need something like this to prevent replay attacks. You can't have really long signatures that you keep considering valid. You need to have, in this case, in order to ensure that the replays can't happen, you need to be able to keep this stuff fresh. But it's been looked at, and actually, if you were doing midpoint beaconing, as in if every point was re-beaconing its path, it would be intolerable. So modelling's been done on origin-only beaconing, and they believe this to be tolerable, and it can be dealt with, we think. Multi-beaconing, though, where you're beaconing from every midpoint, is not going to work. Right? It's too much effort for everybody, and it's not useful, and it's not cost effective. Okay? And that's covered by BGP SecOps. Another draft that was discussed in Quebec was algorithm agility. And actually I'm using this as a good example because it shows you how key rollover happens as well. They took the same premises as how they roll over keys for how they change algorithms. There are a number of algorithms discussed for how these things are signed. And it would be silly to assume that the same algorithm will be used all the time. So if we transition to a new algorithm, we need to be able to do the transition in a seamless way. And we go through a number of steps, and these steps are the same as when you do a key rollover. It's very similar to DNSSEC in this case, where we have a number of phases of acceptance, where you start issuing the new algorithm first. People can start using it if they want. Then you have to be able to do both. And then finally, you don't have to be able to do the old one, then finally the old one's phased out and you go back to the beginning. And that's much on how key rollover works. And then there's CIDR publication. So that's talking about the fact that SIA talks about how the rowers and this information is published. It provides a URI that you then connect rsync to get a bunch of RPKI information out for your cache. If you make updates, there's currently no protocol for publishing back. This draft CIDR publication talks about an XML-based, over HTTP-based protocol for children publishing back upstream. Okay, there's obviously no rsync back because you'd be writing to there's no rsync isn't granular enough to allow those sort of permissions. So this just talks about the publication of it. But one draft that I do recommend that everybody reads, if they read any of these at all, is this use cases. The draft IETF CIDR use cases document talks about what should happen under all of these various circumstances where you've got different types of customers, different types of peerings, what sort of objects need to exist in the RPKI and how they should be validated and what's valid and what's not. It's quite a big document, but and I've just given you a snippet of the index in section 3, the origination use case. It's a very interesting read. It talks about all of these situations and how you would deal with them, or what would be expected to be valid, what wouldn't be valid, what you'd need to do in this situation, what you need to do in that situation. It's a very good document, and if, as I said, if you read any of these, that's the one to read. And finally, some fun. With all these certificates floating around, when there's a problem, who are you going to call? The problem is that the complexity of some of this stuff, it's not initially going to be handled by network engineering people. I mean, if you think about the crossover in your organisation, and it depends on your size, how many network engineering people have to deal with the IRR and filtering and the right database at the moment? And how, a lot of bigger companies have hostmaster departments that deal, or IP departments that just deal specifically with this. How's that going to work with this sort of certification? If you don't have, if you're not big enough to have to justify having a separate hostmaster department to deal with all this IRR interaction, how are you going to deal with all of this? It's probably going to end up being systems people to start with. So the set of contacts for problems with the RPKI objects may end up being different people for who you publish in. Say when you set up a peering with someone, you say these are my contact details, or you use PeeringDB, for instance, which we'll talk about later. The people that deal with the RPKI and the RootSec may be different from the network engineering people that you have listed as peering contacts. So if we sign rowers with our identity certificates, why limit this to just routing data? We can produce a V card for contacts, and we can then sign it back with the EE, and there you go. You've now got trusted contact for this point in the RPKI hierarchy. It's not meant to represent who is. It's just another use of the identity certificate. But it's a good one. It's a fun one as well. Yeah, once you've got the certificate published, there's the idea that you have this Ghostbusters record that talks about a signed B card, and that's someone you can contact for it. How much time do I have, Alexi, left? Where are you? You've got. Okay. Well, I'm assuming I have a bit more time. So I just want to quickly show you some slides from another presentation, which was given. This is some work done by NIST, the US National Institute of Standards and Technology. And can I make that full screen? Don't know how to do that. I'm going to guess. No, that didn't work. Okay, right, so basically this talks about, there's a lot of fear here that adding this sort of complexity to the system is going to impact performance. You can see why the vendors attend a lot of these. They're concerned that they're going to end up building products that then don't have this, that don't scale their control plane in the same way as they can at the moment without all of the routsec overhead. So this presentation made by NIST talks about gives some figures for how they make some measurements and make some predictions about how this sort of stuff can grow and what sort of overheads the router vendors will need to deal with. And it takes two models, edge routers or provider edge routers, which in this case can be considered peering routers, whether they peer with people or whether they provide transit, and route reflectors, which then have to hold on to more and more of these, assuming that none of these route reflector extensions are introduced. So he talks about the low and high watermarks for the number of prefix paths observed, and then produces a ratio of these against the two router types. And then he looks at the update format with these additional attributes and how big they need to be. Now, note of interest that this algorithm, RSA 2048, which is currently being proposed as the more secure algorithm, increases the update size by 15 times, right? Bringing this, you know, in this particular example, bringing this update size up to sort of 1K. Now, just separately to this, there's a draft going through IDR at the moment to extend the maximum message size for BGP, because currently, I'm not sure how many of you know, it's limited to 4096. And you know, introducing these things just like DNSSEC is going to make these updates a lot bigger. So the core protocol needs to be changed to deal with this. So this is the additional overhead, and then he's computed with these two algorithms, the existing ECDSA 256 and the RSA 2048, what these signed update sizes are going to look like compared to an unsigned update. And then he's gone on from here to make some guesses about adoption. And actually, I'm going to move to the linear version of this, which is the cumulative distribution of adoption, starting in 2011 and ramping up through 2016, where they believe adoption really starts. And I believe this data, and I'm not entirely sure, is taken from when router vendors are probably happy to say, yes, you know, we've got a good, robust implementation here. So if the adoptions, which would be about 2014, 2015. So this is based on the adoption starting 2016 and ramping up like this. And I'm sorry, I'm not a statistics person, so I can't talk to you too much about the modelling used here. And then there's based on the PE router for each of these years, IPv4 and IPv6 growth rate, BGP-SEC adoption rate, percentage of paths, prefix paths signed, and then the contribution to RIB memory due to IPv4 and IPv6 eBGP updates on the PE router. And then he goes and
press F12.
Is that the full screen mode? Oh, okay. That's simple. So I don't use Windows machines. And he does the same thing for the route reflector. And then I'm going to show you a graph after this. I think I've put the two together on a graph. That's right. So these are the algorithms side by side for both PE and route reflector. And you can see that because the requirements of RSA 2048 make larger updates and consume more memory, he's got the route reflector curve going up exponentially almost. Well, no, it's kind of like this. It's kind of linear in this phase, up to 32 gig, which is a worst case scenario. Strongest algorithm on a route reflector with that predicted level of growth. The smallest or expected is round about here. So if we look at where we are at around about time of adoption, it's still really nothing spectacular, okay? But actually, looking this far forward, these memory requirements don't seem that large at all. You know, routers that are built from there on onwards aren't going to have issues with this amount of RAM for the RIB. And this is what it looks like in transition. So as we have to do the transition to support both algorithms, we have these step changes, because we have to incorporate the additional memory used to hold the different types of signatures. And that's a signature algorithm transition and a protocol transition. So yeah, anyway, I don't have that much time, so I'd just like to take any questions if anybody has any. No? Okay, thank you very much.